and many of them are planned as well for future. So as I mentioned, one of the challenges is that you'll have to make it more miniaturization. If you look at this picture, I actually show this picture to a lot of people. Do you know what it is? This is the iPhone 5, the entire circuit board of iPhone 5. Why I am showing it? Because this is amazingly done engineering. If you have not opened your smartphone yet, you should go and open it. I will suggest that to do. Of course, it is very difficult to open that, but there are tools available you can buy on Amazon or whatever, Flipkart. It costs about less than $10 to buy those tools to open it. I did open my wife's iPhone because it was water damaged. Then you'll see how what kind of engineering is done. You can see all these different chips. What you can see the antennas. Then how they have done the interconnection. When you are making an antenna, and the antenna itself is not going to do everything. There's something has to come behind the antenna, right? So how do you connect that? How do you put everything together? How do you package the system? So that is called real engineering. So you have to think about that when you are doing your design. So always keep the big picture in mind as a student or as a young faculty. You should always keep that in mind. What I am doing, where is going to go and get used? If no one uses your great antenna that you have designed or great circuit that you have designed, what is the use? Right? So you have to make sure that what you are doing, it has to perform, but at the same time, it meets those requirements that it can be used easily. I can actually make something work great. Two small CubeSats, 6U CubeSat called Marco, and it had antennas. This is just a communication satellite. So what it is to do is that it communicate with the spacecraft using UHF transmission, and then there's the X-band transmitter that is to connect to Earth. But of course, how do you make a big, large antenna fit in on a 6U CubeSat? So this is a deployable reflector antenna. My colleague Nasser Chahat and many others, we actually work together on that and develop this system. And then, of course, there are a lot of challenges involved. Nasser, if you have heard Nasser talking about it, he talked in detail about this kind of stuff. What are the challenges that have to be gone through because it has to be deployed. You have to fold it. What kind of hinges that you are going to use. It is not only about electrical performance. Background noise. So this is another one that we actually developed, another CubeSat. We call it RainCube, the radar on a CubeSat. Oh, let me, sorry. So uh, my apologies for all the background noise. Really sorry about that. So RainCube is radar on a CubeSat. Again, this is a 6U CubeSat. This is a Ka band instrument. There is one of the challenge was to fit in a 50 centimeter Ka band antenna inside a 10 centimeter volume CubeSat. So this is the artistic impression of that. As you can see, that is a 50-centimeter antenna getting deployed, and this is a 60 CubeSat again. And how do you did the design? There's a lot of work went behind. Again, you'll have to think, you'll have to innovate. First thing about the mechanical structure, how do you do the deployment? How do you make sure this is a parabolic reflector? How do you maintain the parabolic structure? And what happens? How do you deal with the edges? As you can see, it's like an umbrella, right? And when you do an umbrella, then your edges are not perfect. So this is not a metal parabolic disc that you see generally. It's slightly different. So what is the effect of those? And then if there is, of course, you have to make sure that your subreflector, there is a subreflector here, and there is a multi-flare angle feed horn that feeds this, and you can see that there are the rims here. So because of the rims, the mesh gets stretched, and this is not a perfect parabolic surface. So how do you take that into account in your design? So you'll have to think about all these and then come up with a solution, and then say, okay, this is the best that we can do. This is very important. Recently, someone they wrote a paper. They wanted to submit it to one of the transactions. Asked me if I could read a little bit and give some feedback before they publish this. And I saw that okay, they did a very good design, and they gave the numbers in the sense, okay, this is the final design, and this is how it's going to perform. What was missing in that is, okay, is this the best that you can do? What is your requirement? They said, okay, my S11 is 18 dB. Is S1 18 dB S11 is acceptable? You said, I don't know where it's going to get used. Then put your own requirement. You said that, okay, fine. Designing something to get gain of this much. Once you do that design, you'll have to also write in your paper that what can you do better? What are the limitations of your design? That what prevents you doing better than what you have done? You can say that, okay, fine, maybe manufacturing is the limitation. Maybe the tolerances is the limitation, right? So if you don't write those things, your paper is not complete, because the reviewers are going to come back and say, okay, you just did it, you have put some numbers, but you know, you have to write those. If that, okay, this is what is happening, this is why I cannot do better, but it's possible to do better, but we cannot do that because of the limit. These are the limitations. So you'll have to think about that when you're writing a paper as well. So here you can see that antenna after it's got deployed, and performance match really well with your simulation and measurement. And you might have seen this. This is the deployment of this CubeSat antenna. This is a cylinder of 10 centimeter, and when you release a kind of spring, and then it gets deployed. And there is a sub-reflector that also gets deployed. And then when you measure this, after it gets deployed, it actually works really well. One of the problems in space that once it gets deployed, you cannot undeploy it, you cannot put it back. So that is one of the challenges. So we also made some even larger antennas. This is 1 meter deploying antenna. We cannot make a larger antenna for this kind of K-band or even go to higher frequencies, because the challenge is too much. Again, when we wrote this paper, we had to write that, okay, what are the limitations of this? Can we go higher frequencies? What will happen if we want to try to go higher frequencies? Can you make it a larger diameter antenna at this frequency? What will be the challenges? You'll have to think about that. You'll have to actually give, when you are writing a paper and trying to get it published in transactions, you should not give the reviewer any opportunity to ask questions, because you have to think, what are the reviewers thinking? What are the questions they are going to ask? And before they ask that question, you put that information in your paper. If you do that, you'll find that most of it will come back in minor revision, or maybe very rarely it happens, accept as is. But it will come back in minor revision, because you are already put yourself in the shoes of the reviewer, and you have answered those questions already. In this thing, as I was saying, that we have to think about the limitations. Like, okay, mesh quality and the surface quality of the mesh. And then can you do it for higher frequencies? What are the challenges? If you want to do higher frequencies, because what will happen, the error that happens because of the non-parabolic structure is too much, then you won't be able to meet the requirements. Of course, you can always make an antenna, but the performance will be poor. So if you have certain requirements, then you cannot make this. So I can of course make this antenna W band, but it's not going to work very well because some of these limitations, and I'll have to write those limitations. I have to mention what are those limitations. How do I fabricate it? How do I make a mesh that gets deployed and it gets the surface, RMS surface that we need? We achieve that. So those are the challenges. And we also have been working a lot of what we have been doing on meta surfaces. Many of you, I know in India, you are looking into meta surface structures. So I had a postdoctoral fellow from, he's a Marie Curie fellow, his name is David Gonzalez. He came from Spain, from Europe. He worked with me and we started looking into some meta surface antenna design. So we believe that, this flat antenna structure has a lot of values. You will find that, even think about it. Suppose you have an antenna that you can design, meta surface antenna, that goes in the back of your iPhone or Samsung phone, and that can give very good reception and directivity. That will be very, very useful. Of course, you are going to say, how am I going to hold this my phone and all? Of course, those are things are there, but there are many applications where flat antenna gives value. Because see, the Marco antenna that we have done is a reflect array, but it needs a feed, which means the volume, the 3D volume of that is not small. But if there is a metasurface design that you can do, where you can make really thin layer of antenna that works well. This is one of the examples. So what you see here is a Ka band antenna, and the height, the thickness of this antenna is about 2 millimeter. Just think about it. 2 millimeter is not much. And we made about 20 centimeter. This is a 20 centimeter diameter antenna. And the feed is at the center. Just there is a circular waveguide feed that generates TM01 mode. TM01 is not the dominant mode a circular waveguide. You all know that T11 is the dominant mode. So you'll have to generate a mode converter that generates the surface wave. So how it works is that if we generate a surface wave using a circular waveguide, that is TM01, then as the surface wave propagates on the surface of this structure, and if you can modulate that surface wave, then it actually radiates very nicely in the broadside direction. So that's what we did on Europa. And Europa is far, far away, right? One of the main challenges that we do not have, like Mars, we do not have a Mars reconnaissance orbiter, that another satellite going around Europa to send data back. So if there is a lander on Europa, one of the challenges, how you send that, how do you send the data back to Earth from the surface of Europa? So that is one of the challenges. So, we started thinking that maybe we will have to have a direct to Earth DT communication system on the lander to Earth. And that needed really innovative antenna design, because you cannot make it very large structure. The lander will has to be small. Then how do you get the gain? How do you, it has to be highly efficient antenna design is needed. So it was considered almost impossible to have antenna design that can land on a small volume on the surface of Europa and send. Europa is the moon of Jupiter, just you might know already. So then there was a 32 by 32 patch array antenna that was designed, and we had a lot of innovative feed ideas. And a prototype, single feed element. We did at 7 gigahertz. This is at this frequency band. We did this is a X band antenna that we designed, and it actually worked really well. NASA was main brain behind this, and few other people again they worked on that, and it worked really well. So So we have now antenna design that can come spectrometer. So think about it. You have a spectrum analyzer in your lab. How much does it weigh? Couple of kilograms. My total instrument mass is 2 kilograms. So I cannot fly a spectrum analyzer with my instrument. So we had to build our own spectrum analyzer on a chip, a CMOS chip. So we did that. We designed that on 65 nanometer, CMOS node, and we fabricated that chip, and it works really well. So of course, because we had a brilliant guy named Adrian Tan, he is my colleague. He did the design. So low profile antenna is one of the requirement. As I said, that you can see here, if you look at this, one of the requirement is a low profile antenna at the front end. So what kind of low profile antenna we can use? As I mentioned, that metasurface antenna is one of the options, that we can actually make an antenna at this frequency band that can go, this is all metal structure that can go on the side wall of my CubeSat that will act as antenna. At 300 gigahertz, the thickness of this is about 200 micron. 150 micron is the thickness of our hair. So this is so thin that you cannot even see. So your antenna is just a thin film on the side of your spacecraft, and that itself is giving your antenna. So it's great, right? We actually fabricated that in our lab at 300 gigahertz and showed that it works. So this is a good concept that might work. So you can use the side wall of your spacecraft as an antenna, and just drill a circular hole, and your system, that is your circular waveguide, of course, and then your system comes behind that. But we also started looking at the efficiency of that is not that great, those metasurface antennas yet. So we looked at some other kind of antennas. One of them is a lens-based antenna with a leaky wave feed. So you can see here that the total height of this is about 7 centimeters. So what you do is you have a leaky wave feed. Many of you know about how the leaky waves work. That is a rectangular, or you can put a circular as well. The waveguide here, and then as the wave comes in, you put in a gap, air gap, and then leaky waves are generated that it leaks and propagates on the side, but then it starts radiating. As it's propagating, it starts radiating, and that goes to a very thin lens antenna that collimates it, and you can get 18 centimeter very high performing antenna here. So you can see a little more detail here. This is the input waveguide, and there is this leaky wave gap I was mentioning. However, since that the air is epsilon r is 1, and then you have to go to a lens which is silicon, there is very high dielectric constant, there will be a mismatch, which means you'll have to actually engineer a material that actually do matching layer, so that it matches with the silicon and air. So we do that, we accomplish that by taking material out from silicon using DRI, deep active ion etching, and then we actually do the matching. And then we fabricated that antenna. You can see here, this is a smaller size. This is actually 7 centimeter diameter, and we measured it and compared it with our simulation. Again, when you did simulation, we have to put down, okay, this is the requirement, this is the gain that we want for our system, and then whether we will be able to achieve it or not, and then we have to put down what are the limitations, what is the maximum possibles, can we do even better than that? If you want to do better, what we needed to do. So those are the things that we had to address as well. And then we also looked at another antenna design. We thought, okay, fine, this lens antenna is okay, but if you put some very thin lens antenna on the outside of our spacecraft, then we'll have to protect it, because then we'll have to put a very small dome to protect this thin lens when you're going to send it out of space, right? Because it might crack, it might, small particles might hit it, and it might, break. So we have to be careful. So that can we also do another kind of design? So we looked into a normal parabolic reflector-based antenna. However, it has to be low profile, because if you look at a parabolic reflector at 20 centimeter diameter, the volume that needed is much bigger, the 3D volume. So to avoid that, what we did, we came up with, you can see here our feed, the subreflected feed is behind this gap, and the subreflector is very close to the parabolic surface. Generally, you don't see, you see that some straws going out, right? And then the focus point is much higher. But we made the focus point very close to the parabolic surface itself. And you can see here we did very innovative design that the blockage is minimum here. So this is at 550 gigahertz, as is for WhatsApp, as I was mentioning. We did the we did of course all the simulations, and then we fabricated it, and we have not tested because we are still under lockdown after the antenna came back. We could not test it because we are not having access to the lab as much and that we like. But you can see here there is some of the pictures of this antenna. And then I was mentioning also that we needed to do a synthesizer. This is a W band synthesizer, a single chip synthesizer that we designed. So this is a W band 90 gigahertz synthesizer. You can think about it. If you have seen your synthesizer in your lab, how big that is, how power hungry and massive that one is. So we replaced that with a W band synthesizer that performs really well, but draws only 200 microwatt of power. So that is very, very small amount of power that it needs because it's a CMOS chip. And then we have a back-end spectrometer. There's 3 gigahertz spectrometer as well. There's an entire spectrum analyzer. Spectrometer is actually a spectrum analyzer that has 496 channels over 3 gigahertz bandwidth. So think about it. If you have set up your spectrum analyzer in the lab, your total bandwidth is span that you are looking at is 3 gigahertz, and if you break that up in 4096, that means about 750 is your RBW resolution bandwidth, and this draws only 1.6 watts of power. This is a huge improvement that allowed us to make the system really small. So as I was mentioning that one of the challenges we had is to do the calibration. That means you need a switch. So in previous generation, how we used to do calibration is we used to use a motor. You can see here, there is we call it field mirror. So we have a motor and there is a mirror comes in. This is a quasi-optical system. So when the motor is out of the way, this mirror is out of the way, then what happens? The signal comes from the sky. There is a parabolic mirror here that send the signal straight to there's a horn here. This is my system. This is my receiver system. This is the synthesizer. And when we using the motor, we bring in the small mirror in front of that, then signal comes and hits this mirror and goes to a load. That's when we known temperature load. So that's how we used to do the calibration. But it needs a motor that needs a lot of power, right? And of course, this is a mechanical, electromechanical structure. So how to replace that with a low loss switch? So we came up with a MEMS-based structure with a switch. So what the MEMS does is, you can see on the right side picture, what you see the rectangular black area, they are rectangular waveguide. And you can see the two arms here. So they go in and out of that rectangular waveguide. You all know that you can change the cutoff frequency of a rectangular waveguide by changing the a dimension of that one, right? So if you put some kind of a septum inside your waveguide, you can change the cutoff. So one waveguide can be cut and the other is open, and then if you move it away, then the other waveguide becomes open and the right side becomes under cutoff. So you can make a switch like that, and you can make a very low loss switch. We actually did that. I'll show you a small video that is working in the lab. It's a very small MEMS structure at 500 gigahertz. I hope it does. It's saying it cannot show the video. I'm sorry. It always happens. We can land Perseverance rover on Mars, but sometimes PowerPoint doesn't work. So otherwise you would have seen, what you would have seen that, this arm going in and out and making this switch work. So that what he did is he replaced all this structure that you can see here on the top left with a very small waveguide based a block that became the switch and the load. So we have saved a lot of space and mass in this design. So of course we needed a load as well. As I mentioned, you can see it's pretty big. This is a room temperature load. So we actually came up with a new idea, new kind of load, that in a waveguide, if you put something and then you can heat it up, you can heat this one up in a very controlled way, then it becomes a load that is a variable temperature load. We call it programmable calibration load temperature. This paper got one of the best Terahertz transaction journal paper award in last year, in 2020. We designed that and it works really well. That integrates with that MEMS switch that makes the calibration system work. So if you put together, you can see here, I'm now putting together the entire instrument. This is my synthesizer, and I'm showing you the 7 centimeter that lens, very low profile lens antenna based system. Here you can see again the mass and power was to meet that requirement, 2 kilogram and 5 watts is a 500 gigahertz. This system can fly to Venus. At the beginning, I was also telling you that we can actually detect phosphine. It needs to work at 274 gigahertz. Did I do it right? You can do the calculation. But so that frequency band, it will work as well. This system will work. So we can fly this to Venus. And then we are putting the WhatsApp instrument together for a balloon demonstration. So this is my CubeSat frame now. This is the antenna. I mentioned this is the reflector antenna, and this is the synthesizer, and we've also built a control system for the spectrometer board that we mentioned. And what you see in front, we have not put that yet. That is this entire front end with the MEMS switch. And this is my instrument, entire instrument that we are planning to fly to go to a comet. We can fly this again to Venus as well. So we are getting ready. So ISRO has a planning and a planned mission to they call Shukran to go to Venus. And there is some talk going on that whether we'll be able to contribute an instrument. If we do, this will be the kind of instrument that will contribute to ISRO's mission as well. So I will end, as I mentioned, I want to keep enough time for you all to ask questions. So I will end, as I mentioned, I want to keep enough time for you all to ask questions. So you can see here that I end with another thing we have done for Perseverance rover is a helicopter called Ingenuity helicopter. It has not flown on Mars yet. It has landed there. It is there waiting. We are actually checking all the systems out to make sure that everything works. And you can see here, so I'll give you some little bit of background. Why we wanted to fly a helicopter on Mars. What is the reason why we are doing it? If you think about it, that our rover lands there and it actually goes around, the total amount of distance a Perseverance rover is going to cover is about 14 kilometers in its entire life. So it cannot really go a lot of these places. So what we thought that if we have kind of a drone or a helicopter that goes with the rover, so it can fly around and look around the crater area that we want to see, and it has cameras and it has other reconnaissance detectors and sensors, and it can send the data back to the rover. It has its own solar panels to get the charging done. Wherever it lands, it gets charged and then fly again. But we want to do a tech demo. The technology demonstrates that it's feasible. So you might ask, what is the big deal? We say helicopter here. and drone flying on Earth all the time. The problem is that Mars, as I mentioned, Mars atmosphere is much lighter, with 1% of our atmosphere, which means to generate the lift that we need for a helicopter, the blade has to rotate much faster, 4 to 5 times faster than the blade rotates here on Earth. For here, we need about 400 RPM for the blades. For on Mars, we need 2600 RPM. And the entire max will be 1.4 kilogram or less. The wingspan for this about 1.1 meter. We need about 220 watts of power, total power for this. So we need to have the solar panels that can generate that kind of power. 220 watts is not that much, 2 light bulbs in a way, if you can think about it. And it has to be fully autonomous. It has gyroscope, it has accelerometer, it has camera, altimeter, all those stuff has to be there so that it can fly on its own, it can get the data, send the data back. So in the lab, we actually did it and tested everything, and it will, you can see here, one of the challenges was that where do we put this helicopter? And then when it sends the data back to the rover, it has to have an antenna on the rover also, right, for receiving. That was one of the challenges. And also, to make the antenna work when the blade is moving around, that was a huge challenge as well. So there was a monopole antenna that was designed, and other antennas that was designed for the helicopter. I don't want to go into details, but the challenge was that how the accommodation, how we put these on the rover. So we had made mock-ups, we did a lot of simulations of that rover mock-up, and then make sure that the antenna works. So this is the picture of the helicopter when it was all integrated and getting packed up to go to Mars, and it has gone to Mars now. And so with that, I will end, and I want to take questions, because I want you guys to ask me questions, and then we can get into more and more details. I think I have to stop sharing, right? How do I stop sharing? Stop presenting. Okay. So if you
Yes,
have
sir.
any questions.
So, yes, sir. There are a lot of questions, appreciation, different messages are there. So, shall I read, sir?
I cannot
What
see
are
any
you on
of
the
them,
questions?
so yeah. Yeah, sure.
Okay,
Go
sir.
ahead and do
Sure,
that,
sir.
because I
So I
cannot
can.
read all these questions around. If you ask me, that will be better. Yeah.
Sure. Sir, the participant Mahadevan asked that is molybdenum mesh the only material for unpure label antenna?
As, can you repeat it? I missed it. The last part.
Yeah, sir. The question is
Molybdenum is the only kind of mesh.
molybdenum mesh the only material for unfurlable antenna? For
That's not. That is
unfurlable
yeah.
antenna.
Yeah, so I understood the question. It's okay. Hi, Dr. Madhavan, how are you? Good that you attended. I know him for a long time. He has
Fine,
worked
sir.
in ISRO and other places for a long time.
Thank
It's a
you.
very good question. Yes, so you can actually look into other materials. We have also looked into materials, kind of of tungsten and other kind of alloy kind of materials as well, so that the requirement for the mesh structure that is there, that of course you need to have certain number of mesh elements per square inch, and also when it does not deforms, so you'll have to make sure that it actually still keeps this its shape well. So other materials we have looked into as well, as I mentioned, some alloys of tungsten and others. So you should look into that. But we found, for at least for this application, we found moly works well.
But for, oh, excuse me, for higher frequencies, the mesh size has to be reduced more and more. So
Absolutely.
definitely with this type of thing, and once they become closer, then the flexibility becomes poorer.
Yeah,
So
that's why
then you have to have a very good mechanical design to do both the things together.
absolutely, and that's why you don't see this kind of deploy antenna at double band yet. That
Yeah.
is that is one of the reason, because we are looking into different kind of antennas for W band, because we thought that this might not be the best possible way forward.
We had one this thing on a 1 meter reflect array which we have used. Was there anything special about it? I think it is not a very special antenna.
No, this actually the main challenge for 1 meter one that we have doing, and we are doing a 2 meter as well, is how do you deploy them. Mechanical part is more important, gets more challenging compared to the electromagnetic part, because you can do a design. Of course, there is some challenge. I won't say there are no challenges, because as you go to the outer elements of that, phases and all the corrections gets more and more challenging, and also the feed so that it illuminates it well. But the main challenge is the mechanical aspect of it. How do you hold it? How do you deploy it? How do you maintain the flatness? And if it's not flat, what happens? How do you actually take care of that?
Thank you very much and wish the speedy recovery for your dad.
Thank you. Thank you.
Yeah. So we can take few more questions, sir, if you permit.
Yes, as I said, I am here. You know, as long as it's needed, no problem. So we can.
Oh, okay. So Niranjan asked that what are the general, in general, the general antenna can we use in terahertz range? Means, might be
Yes,
he's
you can. Yes,
asking
that's a
for.
good question. What kind of antennas we can use? Can we use a microstrip antenna? So you'll have to think about it. Okay, if I'm using a microstrip antenna, what are the challenges? Why I can or cannot use, right? So it boils down to these losses. So as you know that for any microstrip antenna, it has a dielectric material and it has a metal, right? So dielectric, when you measure the dielectric, the tan delta that it gives, what is the tan delta? At what frequency they measure? You'll find most often the number that is given is at 10, 10 gigahertz, 1 gigahertz. They are not at hundreds of gigahertz. So you have to make sure that you find a dielectric material that is very low loss at terahertz frequencies. On top of that, metal ohmic losses go really high as you go in higher and higher frequencies. So the losses are the main challenge for using this kind of antennas at higher frequencies. So if your feed is not very, you can still make an antenna working. You can do high resistivity silicon if you use that very low loss at terahertz frequency. So if you can actually make your microstrip antenna, even then there will be metallic loss, ohmic losses, but you can still make it at terahertz frequencies with low dielectric material.
Well, sir,
Low loss dielectric material.
Deeptiranjan Samant, yes.
Yes,
So
go ahead.
Deeptiranjan Samantale asked one more question that, sir, when we are designing an antenna in terahertz range in any simulator, what kind of feed we prefer?
So it all, you can use any kinds of feed, that, because your simulator doesn't care, right? Your simulator, if you look at Maxwell's equations, it doesn't care if you're doing 1 gigahertz or 100 gigahertz or 1 terahertz, right? So it's about, feed, you can use the port feed. We can use the port feed. That is not a problem for your simulator. So at the end, how do you implement that feed? That will be your, the, you have to start thinking about. In reality, what exactly you are going to put. So we do, that there will be your uh, connectors like SMA connectors. They do not really exist at terahertz frequency. So most often you will find we use a waveguide based feed for this kind of structures, because that is the lowest loss feed that we see most often.
Yes, sir. So one more participant, he is looking for some research topics in antenna. Means your suggestion. What could be the research topics in antenna?
See, so this is a very difficult question to answer for me, right? So when you are doing a first searching a research topic, you'll have to first talk to your advisor. I might suggest something that, okay, build an antenna for me to go to Europa. So it's so it is not going to help you, right? So
Exactly,
instead,
sir.
you'll have to discuss with your advisor your interest, what are the challenges, what are the problem that you're trying to solve, then you'll be able to work on that.
So, sir, there are a few more questions on terahertz, and I would like to ask you one thing, which is also in same line, sir. That the meta-surface antenna you have demonstrated very beautifully, sir. So, what kind of metal and what kind of substrate was used there, sir, in that
So
antenna?
that is all metal. There is no substrate in that. So basically, this is one of the beauty of this, and one of the advantages of this antenna for space applications is that
Right, sir.
there is no dielectric involved. All
Hmm.
metal. So that, and the metal that we use again is kind of alloy, different kinds of metal. We use a laser sintering method of that. So basically, you use a powder of alloy powder. So if you read one of the paper, we actually provided all the details of the materials. And then one of the things is that you should not worry too much about the materials if you are working, making this antenna at this. You can always coat with some. You can do some coating on them, right? You can do some, gold coating to have low loss. But these 3D printers have come a long way. You can do a metal sintering that itself inherently give pretty low loss at K band at least.
Yes, sir. So, sir, so some students are willing to know, or some participants are willing to know that is there any if substrate is required in terahertz antenna, what could be the substrate? Like I have
Yes.
seen in some papers that silicon oxide might be used, and maybe gold can be used as a metal. So,
Yes. So, but again, gold. If we use gold, right? Most at Terra frequency we use gold because it is easy to deposit, right? So, if you look at the gold conductivity, gold. What is the conductivity of gold? If you look at lower frequencies, conductivity of gold, that's the sigma is about 4 e 10⁻⁷ Siemens per meter. So that's what we get. However, as you go in higher frequency, we find that the conductivity starts going down. So at 1 terahertz, you will find it is not 4e7, it will be maybe 2e7, almost half. So gold can be used. In terms of the dielectric materials, we use the best material that you can use at terahertz frequency, low loss dielectric, high resistivity silicon, not low resistivity silicon. You'll find that two kinds of silicons are available. So the most of the silicon that is used for chips and everything, they're low resistivity. But if you have 5K kilo ohm or 10 kilo ohm per square resistivity, if you can get, those are very low loss material, low dielectric loss at terahertz frequencies. So we mostly use that. You can use Teflon, but again, if you're machining Teflon and putting, depositing metal on that, it's not easy. But silicon can be used very easily, high resistivity silicon, and that will work well.
yes, thank you, sir. So there are many more lots of questions
Yeah, go
I
ahead,
could
please,
see in the
please,
chat box.
please go ahead.
Yes, sir. So, Deeptiranjan again asked that what kind of port basically can be used in terahertz antenna in simulators like CST or HFSS?
Yeah, at AFS, I use waveguide port. I use a waveguide, and that means that you are using a normal waveguide port on that. So the feed, the port that we use, a normal waveguide port can be used.
Yes, sir. So, my colleague Oyon asked that, sir, the antenna efficiency obtained from the simulators are not always acceptable. So, which method of aperture efficiency measurement would you suggest?
So this question is loaded in a way because when you are saying that simulation results is not acceptable, the reason is if you are putting realistic parameters in your when you are doing a simulation, instead of doing perfectly electrically conductive PEC structures, if you use, let's say, gold, and you know what is the conductivity of gold, and if you know well what is the dielectric properties of your material, the substrate that you are using, then you are going to get much more realistic results out of your simulator itself. And that's what you should always do. What we try to do is when we do simulation, we try to do a lot of background research and try to put as close as possible to the parameters of the real material at the frequency of interest. And then we do our simulation. That way you can get much more reliable result. of your simulation, and if you measure, you will get very similar answers.
Yes, sir. Shomojit asked, sir, please comment on the polarization of the wave that will be able to communicate DE from Europa.
Yes, of course. When you are doing, always when you do communication, you do not do linear polarization, right? You always do circularly polarized wave. The reason is this: if you are doing linearly polarized waves, then orientation of your antenna, receiving and transmitting antenna becomes a challenge. You have to know exactly which way your the receiving antenna or the transmitting antenna is oriented. So what you do is that generally we always do for any communication system, we generate circularly polarized wave, and that's what we transmit in this antenna that I showed for DT for from Europa. Again, that is actually circularly polarized wave.
So, one participant is asking, sir, that what substrate or what dielectric is best for millimeter wave applications?
For millimeter wave, we can look at some of these drawger materials are applicable for millimeter wave. We can use few other materials like invar can be used at millimeter waves, and also that you can do, as you mentioned, silicon dioxide. You can do nitride materials, silicon nitride. Also, it can be a low loss material, thin if you want to make something thin, dielectric materials at millimeter waves, and you can. So there are quite a few options for millimeter waves, but it gets more challenging as you are moving up in frequencies when you are going to terahertz frequencies.
Exactly. So, Momita is asking, in designing microstrip patch antenna at higher frequency, the feed is always also radiating in nature, which affects the performance. How we can minimize it?
So it depends on what feed you are using. Again, right? When you are going to higher frequency, if you are using a waveguide, as I mentioned, as if you look, I kept on saying, okay, this is circular waveguide, this is a rectangular waveguide. Even for our metasurface antenna, you can use low frequency, you can use a probe feed. But if you are going at higher frequencies, we use a waveguide feed. And one of the good part about waveguide is you do not it's not really radiating from there. So whatever, whenever you're connecting your feed, you know what kind of electromagnetic field you are getting in to your aperture, and you can control that. So it is the radiating from the feed itself is part of your overall design parameter that you have to use.
Yes, sir. Shupan from IIST Shipur is asking that can dielectric resonator antennas really replace metallic antennas in K or K band?
Actually, they have lot of work has been done with the dielectric resonating antennas. So whether they will replace all of it is a difficult question to answer. I don't think you replace all of them, but you can actually make a lot of antennas work very efficiently, very well using dielectric resonating antennas. DRS are you look around, number of references, number of papers that have come out. One of the person who has done a lot of DRA work is also one of the speakers that will be talking in the next couple of days is my colleague Debatosh has done DRA antennas as well. So you'll find that a lot of references are available, but whether will it replace all the antennas? Absolutely not. No, not a single kind of antennas, because every different applications have different requirements. So you'll find. So do not always put yourself in a box that I will only use DRA or I'll only use patch antenna. You should have an open mind. So suppose you are given a problem, try to see what makes more sense. Can I use a DRA? Can I use a patch antenna? Can I use a waveguide feed, reflector antenna? Can I use a metasurface antenna? So do not box yourself in only one way, because you know how to design DRAs. I will use DRA for everything. That might not be the best approach. So if you know how to do DRA antennas, you'll be able to know how to do patch antennas, because at the end of the day, it is all about playing with electromagnetics, right? So you'll be able to do that. So always, think about broad way that okay, what makes most sense for this to solve this particular problem.
Exactly, sir. Dr. Jayabardhan asked that how we use graphene material in simulator, why it is more advantageous over other material. If we wish to use graphene, then what parameters must be considered? So,
That's a very good question. Thank you for asking that, Dr. Yeah, but graphene has, a lot of people are graphene based stuff that people are trying to use. Of course, use it because there is very high mobility, right? You can get very high mobility, very low loss, but you do not see many antennas that has come out that you can really use in practically you can use graphene and it has been used in a practical system. Why? The reason is for sure manufacturing is not that easy. Still, you cannot really do a exfoliation method of retrieving graphene and make an antenna out of that. It's not that easy. Instead, you'll have to, if you really want to make a difference, if you have to really make it work with graphene, you'll have to do CVD grown graphene on copper, and most often it is grown on copper, so that you can actually do photolithographic on that, because you'll have to actually make, you cannot just cut a piece thin slice of graphene and somehow paste it and it will work. So yeah, people are doing that, but that is not the best way forward. So you'll have to see that how do you process graphene. So to my mind, graphene has not really uh, I should not make any comment that could be considered controversial. So I'll have to be careful how I speak. So that's why I'm reframing my answer that so far graphene has not shown as it did not come out the way we thought it would be, for at least for some applications. So for graphene, I think maybe we'll have to still find a niche application where this material property is easy to use. Because one of the challenges is, suppose you are making an antenna with graphene, you will find that the moment you put the graphene on on a substrate, the properties of graphene changes. You will get mobility of graphene extremely high at when it is actually suspended in air. The moment you put the graphene on the substrate, the parameters changes. You are not going to get mobility that high. Suppose you are doing a millimeter wave design, you'll find that most of the time when people are doing a graphene design at millimeter wave, it starts working at very low frequencies, because the change of properties of graphene when it's put on a substrate. So those are that is one of the challenges, right? So again, parameters that you mentioned, parameters are again same thing. What is the conductivity of that material? What is when graphene you are using it not as a dielectric material, you are using to replace some of these metals, right? And then are you going to gain that kind of conductivity when you are putting on a substrate? So that's what you have to pay attention to. And literature, if you look at the number of papers that has come out with graphene antennas, that's where the challenge lies.
yes, sir. Shubham is asking that in millimeter wave dual polarized designs, isolation is an issue. In what ways it can be improved?
It's a problem for all the stuff that we always do, right? We can always crosstalk and coupling. So you'll have to. It is very difficult to give a specific answer to that bit. It depends on what kind of application that you are doing. Suppose you are doing a radar, let's say, a bistatic radar, then a millimeter wave bistatic radar. Then you are transmitting in one polarization, you are receiving in another polarization. Then how do you if you can, for if you are doing in two different polarization, isolation you can improve absolutely, because of the you can take the advantage of polarization. We have designed a grating structure where what we do, we actually convert a a linearly polarized wave. It actually hits a grating structure, generates right circularly polarized signal, and that gets transmitted. The received signal, of course, comes back in the left circularly polarized, and then when it hits the same grating structure, it converts it to other polarization. If it is the transmitted was horizontal polarization, and the return becomes a vertically polarized signal, and then you can actually get 90 dB of isolation. Always the case, because you will not get the separation is the same. There will be some kind of coupling. So main issue is not about the polarization part. Main issue is the coupling part. How do you prevent coupling from one to the other? And that's where you'll have to look at the special application, what exactly you are using, then come up with what kind of isolation that you can provide. I cannot hear you. Surajit, you are muted.
Sorry, sir. Yeah. So I can see a lot of appreciation messages in the chat box and some similar questions like suggestions regarding the papers or project topics. So those questions I'm not actually taking again and
So I
again
won't be
the
able
same
to.
thing.
I won't be able to. Yeah, I won't be able to answer your project topics, because that there are a lot of challenges out there. You have to find what interests you, and
Right,
talk
sir.
to your colleagues and your teacher there or professor. Then they'll be able to suggest what exactly you should work on. But I will tell you one thing: there are many problems out there to solve. That's for sure.
Right, exactly, sir. So, sir, thank you very much, sir, for taking allowing us in the beautiful virtual tour to further to the Mars mission of NASA, then Europa lander. Then sir has also mentioned about WhatsApp systems, CubeSat antenna design, metasurfaces antennas. Sir has also given his insight and very valuable suggestion about the technical paper orientation and writing methodologies. So we are very thankful and fortunate enough, and despite your the medical emergency you're having in your family, sir, all of we are wishing and praying speedy recovery, and sorry for all the inconvenience that caused to you, sir. So
No problem at all. As I said, that I committed to this, and of course I wanted to be here. Then I'll go. That's fine, and thank you for your kind wishes. And again, actually I did not provide many details about how to do the design and everything, because I wanted to give you more of a philosophical talk, that how you should approach whenever you are faced with a problem. If you have many, I know there are many other questions are there. If you want to ask any question, you can send email to me. My email is available on the internet, so go ahead and find, and write to me. I'll be very happy to try to answer when time permits. Of course, if I'm a little bit slow, forgive me, because not because I'm ignoring you, because maybe I'm a little bit busy. So that's why. Okay, thank you very much.
thank you, sir. It's so nice of you. Thank you, sir.
Okay, bye.
Bye, sir. Bye.